Okay, welcome back everyone. In this video, we're going to be talking about the third of Maxwell's equations, which we also call Ampere's Law. Simply put, Ampere's Law is like Gauss's law, but it's for magnetic fields. We say that the surface integral of the magnetic field dotted with ds, a line element, is equal to mu naught times I enclosed, the amount of current enclosed by what we call an Amperian loop. So, remember back in Gauss's law that we had a charge and we constructed a Gaussian surface around it. This was a three-dimensional object that had a two-dimensional surface area. Now what we're going to do is construct a two-dimensional object, a loop, that has a one-dimensional line integral. So, mu naught here is what we call the magnetic permeability of free space. It's like epsilon naught, but it's for magnetic fields. And it has the value of 4 pi times 10 to the minus 7th Tesla meters per amp. Now, you might notice because of the 4 pi that it looks like an oddly specific number, and it is. It's based off of other constants. I is the current in amps. B is the magnetic field in Tesla. And S is the distance around this Amperian loop in meters. And we want to point out that this is a closed loop, not a surface. So in other words, we're talking about a line integral, not a surface integral. And the other thing that we should mention is that most of the time, what we're going to do is just like Gauss's law, where we took the integral of E dot dA, and we rewrote that as E times the surface integral of dA, which just turned into E times A, right? Well, now we're going to, most of the time, write this as B times the line integral of ds. And this means that the line integral of ds is just going to be the circumference of the Amperian loop. In many cases, just simply 2 pi r if we're at a distance of r away. So, again, this is mu naught I enclosed is the integral of b dot ds. And it's used to calculate magnetic fields if we know the current, and most of the time we do. It's the third of Maxwell's equations, and it's a way to quantify circulation. Because of this line integral, which is going around a current, that tells us that the magnetic field is going to be circulating around. And a closer look at this integral, if you haven't studied line integrals before, basically what you do is you take a curved path and you break it up into tiny little pieces ds. And you look at what the field is doing at that location. And it's basically going like this. And we had a lot of symmetry when we did this for Gauss's law. We said that basically E was parallel to dA everywhere. Likewise, B is parallel to ds. And that's the whole point, because we know that from the second right-hand rule, if I have a current like this, magnetic field is going to circulate around my current or around my wire. And this is how we're able to apply a lot of symmetry to use Ampere's law. So this is the third of our 4 Maxwell equations, Ampere's law. Remember the first one, Gauss's law of electricity, that was how much electric flux was going through a surface, and that was Q over epsilon naught. The second law, Gauss's law of magnetic flux, said basically that magnetic flux is equal to 0. Ampere's law is like a flux, but it's more of a circulation. So sometimes it's written in terms of the curl of a function. And coming up in the next couple of chapters, we'll talk about Faraday's law of electromagnetic induction, which is how quickly the flux is changing. Okay, so when we apply Ampere's law, we have to draw an Amperian loop of radius r, and we can go from there. And we often note that the integral of ds is equal to just 2 pi r for this Amperian loop. Okay, so let's do an example. We want to use Ampere's law to derive the magnetic field at distance r from the center of a wire of radius big R, carrying current I naught, where little r is bigger than big R. So in other words, we're looking at an Amperian loop, which is outside of our wire. Okay, so this means that the current, which is enclosed by our Amperian loop, it's not a surface anymore. It's not a sphere like Gauss's law. It is a loop. So it's just a circle. And you just think about how much current is inside of that loop. Well, it's just I naught. So Ampere's law says that the integral of b dot ds, let me clean this up, is equal to mu naught I enclosed. So b times the surface integral of ds is equal to mu naught I naught. And if we're talking about a loop that has a radius of little r, then that means that the integral of ds just simply turns into 2 pi r. And this is why what we introduced last lecture is true, that the magnetic field of a current carrying wire is simply mu naught I over 2 pi r. Now there are ways to get to Ampere's law from more basic principles, but that's sort of beyond the scope of this course. But notice that this is what we said the magnetic field was for a current carrying wire. So that's really cool. Now so there's our Amperian loop. Now we're going to do the same thing to derive the magnetic field at distance r from the center of the wire, where we are inside of the wire. So now this is our Amperian loop. So we don't have all of the current inside of that loop because the entire shaded region is where the current is. Okay, don't pay any attention to the little x. That just means that the current is coming or going into the page, which means that the magnetic field is going to circulate counterclockwise. Okay, but we have current spread all over this wire. It's not just a 1D object, but we have constant current density J, which, if you remember from a previous unit, is current per area. Okay, so if we want to talk about I enclosed, we would have to divide by A enclosed. Now it turns out that I total is just I naught, and A total is pi big R squared. It's just the area of that cross section. I enclosed is what we want, and A enclosed is going to be pi times little r squared. So this right here is little r, and the entire thing is going to be big R. This means that I enclosed is going to be I naught times r squared over r squared, little r over big R. And this might remind you of when we had charge spread out in a sphere, where we said that charge enclosed was q times r cubed over r cubed. And that was because we had a sphere, so we had a volume, which was 4/3 pi r cubed. Now we just have an area, which is pi r squared. Okay, so let's apply Ampere's law. Integral of b dot ds is equal to mu naught I enclosed. So it's very easy to set up. B times the integral of ds is equal to mu naught I naught little r squared over big R squared. So that's I enclosed. Again, the integral of ds going around this Amperian loop here is just going to be 2 pi r. And that's mu naught I naught r squared over r squared. One of those will cancel. And we are going to get a magnetic field of mu naught I naught r over 2 pi big R squared. Now notice a couple things. One is we have to have continuity with the previous example. So when little r is equal to big R, we have the same thing as before. We have an r there, but a 2 pi r squared here, and that's the same thing that we had. Secondly, let's think about a graph of field versus radius, and here's big R. What happens when we're inside? Well, it looks like it is a linear function with respect to r. So it just linearly increases until we get to r, and then it falls off as 1 over r. So here's another view of that. We have a linear increase, and then we have falling off as 1 over r. Okay, so next time we're going to be applying Ampere's law to a couple of other situations, including the solenoid and the toroid, and we're going to talk about a very important concept called the displacement current.